myself Dr. ATHIYAMAAN from the Department of Civil Engineering, Assistant Professor. Okay, so I'm here to teach you about solid mechanics. Okay, so the prerequisite subject of the solid mechanics is nothing but elements of civil engineering and mechanics. So in elements of civil engineering and mechanics, we might have studied about the rigid bodies, means there is no deformation. We might have studied about the loads and the reactions. We might have now considered about the material properties, what kind of material that particular material that is having. But when it comes to this solid mechanics, we are going to consider about the material properties, means what is going to be the elasticity of that particular material, and what is going to be the strain. If I am applying some load on the material, how much it's going to deform for that particular load that has been applied over that material. So we'll go into the subject. First, let us see what is there in our solid mechanics. I'll go through the syllabus. Okay, what and all we are going to study in this solid mechanics. Then we'll go to the introductory part of our solid mechanics. So this is our syllabus where we have, this is our course objective. We have the module 1 and module 2. In module 1, we will be studying about simple stresses and the compound stresses. And in module 2, we will be studying about shear force, bending moment, and the analysis of simple trusses. Okay, so this content we will be having in our module 1 and module 2. And we have module 3. In module 3, we will be studying about bending and shear stresses. Means how the beam is, or how the object is going to react in over the bending when particular load is being applied over your structure. Then we have torsion. So it's how the, if I am applying some load in view of torsion, how the material is going to behave. So that we will be studying in our torsion. So we have torsion of circular and hollow shafts and those elastic theory of those torsions, stresses and the deformation in circular solid and the hollow shafts. So this we will be studying in the topic of torsion. In module 4, we will be having thin cylinders and thick cylinders. So especially like if you are filling your cylinders with some pressurized air, how the cylinder is going to behave, what are all the stresses that particular cylinder is going to have in terms of the direction, in terms of quantity. We'll try to look into this thin and thick cylinders. That will be in your module 4. So in module 5, we'll be studying about columns. Okay, so it's one of our important topic, because when those are doing on structures, that is especially our civil engineers. So this solid mechanics, when it comes to beams, trusses and columns, it is very important. This is going to be your carryover for your higher semesters, where you're going to study about the determinate structures, analysis of indeterminate structures. So this is the core foundation of your upcoming semester subjects. So try to concentrate here. So these are all going to be our course outcomes, where you can be able to study about, explain about the trusses, strains, and the determines its components on the inclined planes. Okay, when it comes to trusses and the strains. Okay, and the analysis of determinate beams. So when it comes to here solid mechanics, we are just going to deal with the determinate structures. Okay, we are not going to concentrate on indeterminate structures. So indeterminate structures, we will be looking into those indeterminate structures in your higher semesters. So in your elements of civil engineering and mechanics and the solid mechanics, we are just dealing with the determinate structures. Means we can able to analyze our unknowns that is being developed in your beams with the available equilibrium equations. So that is nothing but summation of force along x-axis and summation of force along y-axis, and the moment that is coming into your system will be equal to 0. So that's how we are trying to classify our determinate structures, where you can analyze your beams with the available equations. So that is nothing but your equilibrium conditions. Okay, these are all the recommended textbooks, and this is going to be a question paper pattern for your autonomous syllabus. Okay, let's go into the subject in detail. We'll try to discuss from the scratch. Okay, so mechanics. So when it comes to mechanics, we have the branches of your mechanics where it has rigid bodies, deformable bodies, and the fluids. So here we are going to study about this deformable bodies. That is, in deformable bodies, we are going to concentrate on determinate structures alone. So rigid bodies, you means that there is not going to be any deflection or bending. If the material is going to break, it's not going to deflect, so it's going to break, okay, without giving any deformation. So in your mechanics, that is engineering mechanics, we have studied about rigid bodies. Okay, so we assumed the body that I am going to analyze is a rigid body, and we have analyzed it. Okay, we have tried to calculate our reactions in our engineering mechanics, that is elements of civil engineering and mechanics. So when it comes to deformable bodies, that is nothing but your solid mechanics. We are going to consider your material properties, how your material is going to behave to that particular load in terms of stress and in terms of strain. So you are going to concentrate on the deformable bodies in your solid mechanics. Next, fluids. Okay, so that is also part of a mechanics where it will be under the different branch, that is nothing but fluid mechanics. So further we have static and dynamics, okay, and incompressible fluids and compressible fluids. So that comes in the topic of fluid mechanics. So here we are going to concentrate on deformable bodies, right? Okay, so this is going to be the content that is going to be in your first module, that is first half of your first module, that is simple stresses and strains. Okay, so we'll be studying about elasticity and plasticity, what are the different types of stresses, different types of strains, and main thing is we'll be studying about Hooke's law. That will be very interesting. Hooke's law we have, and stress and strain diagram for the mild steel, that is very important for civil engineers because we are going to deal with the steels. So we should be knowing how your steel is going to behave when a particular load is applied on the steel. So based on the stress, how much is going to get strained. So that we'll be studying in our mild steel. That stress strain graph we'll try to do. Then working stresses and factor of safety. So when you see here, we have factor of safety, that is very important. So we are not going to give a complete load that is particular material is going to bear. Suppose if I take some object, if I take, this is my pen which is a column, suppose it's going to take if I'm going to test, putting some experimental test on this column, considering this as a column, if it's going to take some 100 kilonewton, if it's the particular pen is going to take 100 kilonewton, I'm not going to apply 100 kilonewton and design. Okay, there is a term called factor of safety. So I need to be very safe. Okay, we are all should be in the safer side. So I'll consider some factor of safety and I will give that, and I will design it for that particular load. So I won't take as 100 kilonewton and I will design. So I will reduce that particular small portion. So how much portion should I reduce? There is some systems that we will look into it. How do you consider that factors? Okay, how much should be the factor of safety that to be considered for that particular material? If it is steel, how much should be? If it is a concrete material, how much it should be? Okay, so that we'll be studying. And we have lateral strains, and we have Poisson's ratio and volumetric strain, elastic moduli and the relationship between them. Okay, bars of varying cross sections. We have composite bars, temperature stresses, and strain energy, and resilience, and gradual and sudden impact and shocking loading. So these are all the few concepts that we'll be studying in your simple stresses and strain topic. Okay, apart from that, we have other mechanical properties of your material. You can just see here, that is nothing but ductility, brittleness, toughness, malleability, behavior of your ferrous and non-ferrous materials. Okay, ferrous and non-ferrous is nothing but a steel. Okay, steel and non-steel, which is not having that ductility property, that falls under non-ferrous material. So it will have a brittleness in nature while it is breaking. So these are all some few topics with the respective to the mechanical properties we'll be looking into. Okay, so what is the main aim of our mechanics of solids? Okay, so we are trying to predict how geometric and physical properties of the structure will influence its behavior under severe conditions. Okay, if I'm applying some particular load to the particular material, considering those properties, material properties, how it will behave. That's what we are trying to look into in this particular subject, how the material will behave for that particular properties. If a material having the steel, that is ferrous material, if I'm applying some load, how it will deflect, how it will deform, how much will be the strain. So those things is our going to be our aim in this particular subject. Okay, let's take some example here. Okay, so let me say this is my sample, this sample S, I have a sample S. So first thing is stress. What is the stress that we are trying to study from our PU? The stress is nothing but load applied over that particular cross-sectional area. Okay, so this is my specimen. Okay, let me take the sample as yes. I am trying to apply a load over this. Okay, so I have a handle wheel. I am trying to apply a load here. Okay, through this screw arm. Okay, and we have a cross head. So over this, I am trying to apply a load. Apply a load on this section. Yes. Okay, so this is my sample. I am trying to apply a load. If I am applying a load here, okay, so what kind of force that particular stress this particular sample S will experience? So you can see here, this is nothing but your axial compression. This is nothing but your axial compression. So the particular sample is being compressed. The particular sample is being compressed. So that is nothing but your compression stress. Okay, that's nothing but your compression stress. Okay, so let me take a sample of your, let me take this as your concrete. So let me take, this is your concrete sample. Okay, let's try to study something about stress. Okay, okay, this is my concrete sample. So let me take a concrete. I am trying to apply a load. Let me take load as P. So this is nothing but your concrete sample. Okay, this is your concrete sample. So let me have a flat form here. Let me have a flat form. So of course there will be a force that being developed. That is nothing but your normal. Okay, I am applying a force N here. Okay. So what is stress? Stress is represented by sigma. Stress is represented by sigma. It's nothing but load that is being applied over the cross-sectional area. So that is nothing but load by cross-sectional area. Okay, this is nothing but your cross-sectional area. Cross-sectional area. Okay. So now, what kind of stress this particular sample will experience? Okay, so what will happen if I apply a load over the sample like this? Okay, I'm applying a load over the sample like this. What will happen to the system, to the sample? It will get compressed. Okay, it will get compressed. Okay, so it will, so initially if the size is this much, if the size of the sample is this much, so After applying the load, what will happen? The size will eventually be reduced, right? The size will be eventually reduced. The size will be eventually reduced. So how much it will be reduced? How much it will be reduced? That will quantify. Okay, that will quantify with other parameters. So this much, if this is my total length, if this is my total length L, if this is my total length L, let me take length DL is reduced. Amount DL length, this much amount is being reduced. Okay, this much amount of length is reduced. So this particular stress is nothing but your compression test. Okay, compressive stress. Okay, this is nothing but your compressive stress. And of course, if a particular material is being applied stress, of course, I will get strain. No, this material will get strained. Okay, like if I am applying some stress, of course, it will get strained. Strain is nothing but how much deformation that particular object has undergone. Okay, so in that context, this much amount, how much amount DL. Okay, the strain is represented. Okay, epsilon, we represent it with epsilon, and how much it is? Change in length by its original length. Okay, so since it is compression, we are giving it with letter C. Okay, so it is going to it has undergone compressive stress, and the respective strain, how much is the deformation that has undergone, is nothing but your strain, that is compressive strain. So change in length by actual length. So this is nothing but your stress and strain. Stress and strain. So stress is nothing but load by area, and strain is nothing but change in length by the original length. Okay, so this is compression. So same tensile. Okay, tensile stress and respective strain. Okay, so same, let me take the same object as the example. Okay, let me take same concrete. Okay, in this context, let me take, I have a concrete. So I have a load that is being applied, that is trying to pull my concrete. Okay, stating it is in the equilibrium condition. Okay, means if particular load is being applied here, same amount of load will be applied here. Okay, in order to keep the system in a equilibrium. Fine. So same. Okay, over this cross-sectional area. Okay, the definition remains the same. So stress, of course, how much is the stress particular object is undergone? Nothing but load by cross-sectional area. There is no doubt in it. Okay, it is load by cross-sectional area. So what kind of stress that particular object has undergone? Tensile stress. Okay, tensile stress, because it is being pulled. Okay, that particular object will experience a tension. Okay, it will experience a tension. Okay, so if this is the original length of that particular object, so I applied a load like this. Okay, so if this is my length, L. Okay, after applying load, what will happen? The length will be increased, right? How much? We don't know. We'll try to quantify. Okay, as a civil engineers, we have to quantify how much exactly it has gone. Okay, that we'll try to calculate. So first we'll understand the concepts here. So this much amount, okay, this much amount has got elongated, dl. So I am giving it with letter dl. So this letter DL. Okay, this is the extension of the line. Fine. So same strain we are representing with sigma T and epsilon T, which is equal to same. How much it is? DL by L. But it is a tension. Strain is in terms of tension. We are trying to pull it. Okay, so we have tensile stress and tensile strain. Okay, so this is with respect to stress and strain. So we have compression and we have tension. Okay, so the definition remains the same, but based on the application of your load, so the statement varies whether it is going to undergo a tension or a compression. Okay, and we have one more type, that is called, we have shear stress and strain. Shear stress and shear strain. Okay. So we can, let me take a small framed structure. Okay, let me take a framed structure. So let me name it as A, B, C and D. So this points. Okay. Now I am trying to apply a load. Okay, I am trying to apply a load here. Okay, I am trying to apply a load from this direction. So what it will do to the structure? It will try to make a sway. Okay, it will try to make a sway. Okay, it will try to push this structure away from its original. Okay, how much that will quantify. Okay, let me take this as theta. Okay, so first of all we should understand what is shear. Okay, so the concept remains the same for stress and strain. Stress is nothing but load by area, and based on the application of your load, the term varies whether it is going to be compression, tension or a shear. Okay, so let me take a pack of cords. Okay, so let me take a pack of cords. Imagine I have a pack of cords in my hand. So I'm going to apply a load vertically. Means what? I'm trying to compress the whole pack of cords. Okay, I'm trying to eliminate the voids that is trapped in between your pack of cords. Okay, so I have compressed it. Okay, what kind of stress it has undergone? Compression stress. Okay, similarly if I try to pull it, I'm trying to create a void in between your pack of cords, means it's undergoing tension. Fine. So now I'm trying to apply a load, okay, in this direction. Okay, apply a load in this direction. So what will happen? I will try to divide the pack of cords. So in this particular surface area, if I am trying to remove the pack of cords, the surface area, okay, so that area is undergoing a shear stress. Okay, if I am trying to apply a load like this, okay, I am applying a load like this, so I will divide the pack of cords, right? So while I am dividing, this particular surface that is undergoing a shear stress, if I am trying to remove it, that particular surface will undergo a stress that is called shear stress. Same thing is happening here, but it is, let me take these points are all rigid points. Okay, so what will happen? It will try to tilt away from its original. Okay, let me take it as total length as L. Okay, total length as L, and how much it has got moved from its original position. So that I will take it as DL. Okay, so how much it has undergone? Of course, we are representing, this is strain. Okay, strain DL by L, and the stress is nothing but load by cross sectional area. Okay, so today we have seen about stress and strain. What is stress and what is strain? And we have three types of stresses and three types of strain. What are those? We have compression stress, tensile stress and shear stress. So the respective strain that has undergone for the stresses, we are terming it as compressive strain, tensile strain and shear strain. Okay, so this is what we have seen today. Now we will see how Hooke's law. What is Hooke's law? Okay, it is very important when it comes to civil engineering point of view. We should understand what is Hooke's law. Okay, okay. So we'll see about Hooke's law. So we'll see what is Hooke's law. So it is very important to understand the material properties. Okay, so what does that Hooke's law states? Hooke's law states stress. Okay, stress is directly proportional to strain. Okay, so what is stress? Sigma is directly proportional to strain epsilon. Okay, so in order to remove this proportionality constant, we are adding a proportionality limit. Okay, so what is this proportionality limit? It is nothing but letter E. Okay, so E is nothing but Young's modulus. Okay, E is nothing but okay. So E is nothing but Young's modulus. Modulus is nothing but some constant value that particular object will be having. So if I say steel, steel will have a particular Young's modulus. If I say concrete, it will have a particular Young's modulus. So that is nothing but your proportionality constant. So we are trying to quantify the things, right? So we'll try to with the material properties, we'll try to calculate how much is going to be the deflection. So in terms of DL, we have seen what is strain and what is stress. So we are trying to quantify it. So what is stress? Stress is nothing but load by area, and we have E. And what is strain? Strain is nothing but change in length by the actual length. Okay, so now I want to know what is your deformation. So what is the deformation that has occurred in a particular system? So DL. So having DL here, I will take the other components to the other side. So we will have PL by AE. Okay, so PL by AE. So this is your important formula that you have to remember to calculate how much is the deformation in terms of stress or in terms of strain based on the load application. We'll try to calculate here. So Hooke's law, what does that state? Stress is directly proportional to strain. So what is that? So suppose let me have a material. Okay, let me have a material. So let me take load. Okay, let me take and strain. Okay, strain, how do you say? DL. Okay, load. Okay, okay. So let it be in terms of Newton, and deflection let it be in terms of mm. So here unit is very important. So what is the unit of stress? Unit of stress is nothing but Newton per mm square. So if you're calculating in terms of mm or in meter, but it should be in terms of square, mm square, meter square. Okay, because why? Because it is nothing but force. P, unit of force is nothing but Newton, and the SI unit of area, cross sectional area, you are going to measure. If this is your cross sectional area, if this is going to be a cross sectional area, you will be measuring. So if you are taking this as your width and this as your breadth, so you will be calculating W into B. So it is nothing but mm square. So the unit of your stress is nothing but mm square. Similarly, what will be the unit of strain? What will be the unit of strain? You look here. So dl by L. So change in length is going to be in terms of mm. Okay, your length is also going to be in terms of mm. So it has no units because this unit and this unit may get cancelled. So You need not to mention the unit. It is nothing but no units. Okay, you can give no unit. Okay, strain. Fine. So let me calculate. Let me tell you what is this stress and how do you calculate related with this Hooke's law. Okay, I have a system. And I'm going to apply a load. Okay, let me take. We all would have come across the compression testing machine. So if not, you can go to your lab and see what is the compression testing machine or UTM, universal testing machine. So I am going to keep my sample in my universal testing machine. So I am going to apply 1 Newton load. Okay, 1 Newton load. Okay, if I apply 1 Newton load, how much is going to be the deformation? Okay, so let me take for 1 Newton, I will calculate. Okay, for 1 Newton, let me take the deformation is 1 mm. Okay, deformation is 1 mm. Similarly, when I apply 2nd Newton, again deformation goes to 2 mm. Okay, deformation goes to m. So it is linear. So if you see for 1 Newton, 1 mm is deformation is 1 mm. So other than 1 Newton, 1 more mm is getting reduced. So the stress that is being applied is directly proportional to the strain, that is change in length by actual length. So how far? So Hooke's law defines it, how far it is directly proportional. So as long as it is directly proportional, your Hooke's law is valid. Okay, so this is what Hooke's law is trying to say. So if I am trying to draw a stress strain graph, okay, this is my stress and this is my strain graph. Okay, so this is the typical, this is your typical stress strain graph for your mild steel. So what does it say? Your Hooke's law. So till here it is directly proportional. So till this point your stress is, till from here to till here your stress is directly proportional to your strain. After that it behaves differently, an intermolecular displacement disarrangement takes place and it is varies. Okay, this is the other part. We'll try to study when we are trying to study the stress strain graph for the mild steel. So this till here your Hooke's law is valid. Why? Because your stress is directly proportional to your strain. So in that context we can able to find your deformation. So your deformation you can find till your Hooke's law, where your Hooke's law is valid. Okay, so in your experiment you can try to visualize. Okay, in your experiment, that is in a UTM, you can try to visualize while you are calculating your stress and strain graph for your mild steel. So it will be doing in your using your UTM machine. Okay, so next class we will be further trying to study about complex stresses and the stress strain graph of your mild steel. Okay, thank you.